So when you're looking at a flow problem in a deep soil, um, there's certain things that are kind of limiting cases that are really important to keep in mind. And one of them is what we call unit gradient flow. So what do we mean by unit gradient flow? Well, remember, if I find one solution to our differential equations, then I have found the solution to our differential equations. So let's just take a little case. We have a guy standing up here, or a person standing up here, and they're holding onto a hose, and they're applying water very uniformly over the surface. So they're applying water all over the surface with their hose. And they're having a constant flux, Q. Okay? So we have this situation where it's a constant flux, and the water table or any limitations far, far down. And this person is extremely patient, and so they keep on applying water until the whole thing is at steady state. Now, I say, and I'm just going to claim this, and then all I have to do is show that it solves the solution, it solves the equation. I say that Q equals K minus K of H times the d capital H dz. Okay, this is Darcy's law, of course. But what I'm going to say is, okay, Q equals minus K of H. Remember that H is equal to little h plus z. So that's going to be equal to dH dz plus 1. Okay? Now, what if we have H equals a constant? After all, the same flow is going everywhere, so shouldn't the soil be at the same pressure everywhere to carry that same amount of flow, to have the same conductivity? So let's just see, is H constant? Does that work for us? If H were constant, then guess what? dH dz is equal to 0. And what we get is the gradient here equals 1. So we now have that Q equals minus K of H. And you'd say, well, what about this minus sign? Well, that's because Z, of course, is upward. And so Q is, in fact, a negative flux. It's going downward. And this is what happens under steady state with unit gradient flux, because the Q is constant everywhere, K is constant everywhere, H is the same everywhere, so it's consistent. Q is constant, H is constant. That solves this equation, which is solving Darcy's law. Therefore, if we have one solution, we have the solution to Darcy's law for this, for the differential equation. And interestingly, let's just say that K, use our old friend Gardner. Let's just say that. Then we have Q equals Ks exponential of alpha H, okay, with a minus sign, of course. And so we can now solve for H. So we can say Q over Ks equals exponential of alpha H, take the logarithm of both sides, and we get that, and divide by 1 over alpha, so 1 over alpha, the log of minus Q over Ks equals H. So what this is saying then is that for a constant flowing situation, we can say that for that flux and that conductivity of soil and the soil with this retention function, that will be the pressure. So it's a very powerful result. The point is that in many, many deep vadose zones, under reasonably constant flux, so deep in the vadose zone where it's averaging over the whole year worth of big rainfall and small rainfall, it all averages out going downward, we end up with a unit gradient. And that unit, the value of the pressure that's consistent throughout the column will be a function of the flux. The higher the flux, the closer to zero the pressure. The lower the flux, this goes to minus infinity, and the more negative the pressure would be. So here we have an expression that gives us the pressure potential as a function of the rate of flow, the conductivity, and alpha. And so this concept of unit gradient flow is very applicable to deep vadose zones, and it gives rise to very simple predictions where if you measure the pressure in the soil, you could actually estimate the flux, which is a neat little trick in looking at desert environments.